Hi, welcome to the Earth Science Classroom. We are in the astronomy playlist looking at Kepler's third law. And this law is, well, this video is going to look at certain things. We're going to look at the link to both the first law and the second law, and how they combine, how Kepler worked through these different progressions of his laws to culminate in this third law. So what is third law? We'll do that. What it means, and also how it relates to the future theory of gravity, or not theory, but the law of gravity. All right, join me now. All right, so a little recap. So in 1609, Kepler had his first two laws devised, published, and the first law was law of ellipses, that the orbits were not circular, but slightly squashed, therefore called ellipses. And you have a major and minor axis based on the bulge or the difference in shape. And these ellipses are drawn through two foci or two focuses. In which gravity is focused upon, in which the planet is going to revolve around, and that causes there to be a position of the planet where it's closest to the sun in relation to our system, the center of gravity, where it's called the perihelion, and a position that's very far away, which is called the aphelion. Now, a way to measure the amount of elongated shape of the ellipse is called eccentricity, and that's a scale from 0 to 1. 0 is more circular, and 1 is more elliptical. Most of the planets are between 0 and 0.2 eccentricity, so they're very, very circular, but not exactly a perfect circle. It still has two foci. And this was happened 9 years after Kepler was hired by Brahe. Kepler, unfortunately, was left to do it himself once Brahe passed away in 1601. But then Kepler used all of his math and math knowledge in conjunction with Brahe's notes and observations. Then, once the first law was done, the second law was kind of like the follow-on, the second act, so to speak, whereby he saw that there was a change in velocity of the planets as they revolve around the sun. In particular, this was Mars that he looked at in particular. And that when the planet was in the position or closest to the sun, which is the perihelion, the planet actually moved faster on the orbit and covered an area in this orange triangle as shown right here, right here, this triangle here. Let's go triangle A. And then obviously when the planet is in the position of the aphelion, that it will go a bit slower and again travel a bit less in distance, but because it's further away from the sun, that area of the triangle is the same. So it's the same area as A. Even though different shapes, they still have the same area. So in order to have this equal area, the planet had to change speeds. When the planet is closest to the sun, it went fast. Far away from the sun, it went a bit slower. And this was all in conjunction with the 99 years of the scientific revolution. And then in comes his third law. This happened in 1619, so it's like a 10-year gap after the first, obviously, two laws were shown or published to the world. And 10 years later, he came up with this third law, which is law of periods or law of harmonies. Now, periods in this case refers to time, duration. Harmonies is in terms of the pattern and how synchronized the planets are, or he found them to be. So using the data that he had collected over the 19 years of working with Brahe, well, first working with Brahe and then obviously working by himself on his laws, he noticed and he collected all data from all the planets. Okay, and found that there was a pattern, not only with Mars and Mercury and Venus and the closer planets, but he found a pattern between all the planets, including Pluto. So the 9 in total. And what he found was there was a relationship. There was a relationship between the orbital period or the revolution, the once around the sun, and the distance of that planet from the sun. So depending on how far that planet is, there was a correlation, a relationship of how fast that planet would revolve and orbit around the sun. And he then produced a graph and then started to basically tinker with the data, try and find a mathematical formula that fit both the time, the period, and the distance. So this was his data table. And he started obviously with the closest planet to the sun. So we're going further away. So we're increasing distance from the sun. As we can see here with distance. So it is increasing as we're going down the vertical column. Also, the same relationship. The time it takes each planet, including dwarf planet, which is Pluto, the time it takes to complete one revolution around the sun. So again, here's our sun, here is our planet, planet X, and one complete revolution around the sun. Now, this does not include anything or relate to anything about the rotation around the planet's axis or the tilt. It's just purely the time, the distance. So the distance from sun to planet X. And we know that distance from Earth to the sun is 1 AU, or astronomical unit, or the average of 93 million miles. So we use the AU as a simplified unit of measurement rather than using miles or kilometers, because it just gets messy with the large numbers. And you can see here, Earth is 1. There we are, distance is 1. So it's all based on the Earth's distance. Now, if you take the periods increasing, distance increasing, and what it did was, period is T. Distance is R, or the radius. So what he did over the course of the 10 years, he was trying to formulate different ways to work this out, and he found that if you squared the distance, squared the time, so time squared, and then you cubed the distance, okay, they equal each other out. They equal each other out. For example, if the time period was 8, so 8 squared equals 64. Then the distance was 4, and if you cube 4, it equals 64. 4 times 4 is 16, 16 times 4 is 64. So what you have here is the correlation between the time and distance is pretty much, as you see in this column right here, is damn near close to 1 or is 1. That means that all these planets are revolving at the correct speed according to how far away the planet is to the sun. So what did Kepler's third law basically say? Well, everything is in harmony, everything is in order, everything is going around the sun at the right, according to distance, at the right speed. Nothing is out of place, nothing is irregular. Nothing is a strange anomaly that you can't figure out, because the sun, being the heliocentric model that was now, the agreed upon model, this sun in the center and the sun being so large and so dominating for its size, that he saw that everything just lines up. And this was 70 years before Newton came around and put gravity into the mix. This is basically showing that gravity is the universal glue or construct or structure that is holding our solar system in place, because the sun's gravity is the dominating force. It's 99% of the mass, therefore it's the majority of the gravity. So the sun's gravity is basically, wherever the planets are into the distance away from the sun, how many AU they are orbiting at the right speed for their distance. There's not one planet that's going 85 times faster on a certain distance. It's all lined up because gravity is consistent. Gravity is working on each planet based on the distance and the strength of gravity. Therefore, it's orbiting at a certain speed. So he linked up the planets' patterns, and they're all synchronized without really knowing gravity, but he basically saw the effect. He noticed and reported the effect of gravity without actually stating it. All right, so guys, hope this helped you with the third law and helps you with the mix, combine the first, second, and third law. And obviously, we're going to look at Newton as well in another video, and how we understand how our system around the sun, our Milky Way galaxy, and our universe kind of works with that universal gravity.